Okay, hi everyone. Welcome to back to our one word seminar. So today I'm very happy to have Professor Kathryn Lindsey to give us a talk on her recent work on ReLU networks. And Kathryn is an assistant professor in Department of Mathematics at Boston College. And by training, she is a pure mathematician with expertise in dynamic systems and low-dimensional geometry and topology. She got her PhD from Cornell and complete a postdoc in mathematician and in Chicago. And then she recently get into the deep learning part with her rich experience in mathematicians and theory. And her research recently focused on the geometrical and topological properties of feedforward ReLU networks, which will be given in this talk. So without further ado, let's welcome Kathryn's talk.
Well, thank you very much for the lovely introduction. And thank you to the organizers for the opportunity to speak here. It's really a pleasure to meet this group and have the opportunity to talk to you about some of the things that I've been thinking about recently. So my talk is on my iPad. So I can sort of write as I go. And thank you all for attending. If at any point anyone has a question, please feel free to just unmute yourself and just like interrupt me. In particular, if I use any jargon or notation that's not clear, please stop me because I'll be happy to clarify anything. Okay, so I'm talking about images and fibers of the realization map for feed-forward ReLU networks. And before I forget, I want to start by acknowledging that my talk today draws on various joint projects with collaborators. And so I've stolen their photos from the web. In various combinations, this material is from work with Ellie Grigsby, Marissa Masden, Rob Meyerhoff, David Rolnick, and Chen-Chi Wu. Okay, so feed-forward ReLU networks. First, I want to establish the object that I'm talking about today. So here's sort of a picture of what I imagine a feed-forward ReLU neural network looking like. Mathematically, I think of it, I'm going to use the following notation. My domain is going to be Rn0. Then there's some number of hidden layers. And then the output is Rnd, D for depth. So it's a function from Rn0 to Rnd of a specific form. So the form is that the function is a composition of layer maps, where the layer maps are each of the form sigma composed with an affine map. I'll make precise what I mean in a moment. But first, let me say that I'll use the word architecture and denote it N0, N1, etc. up through Nd to denote the dimensions of these spaces. So N0 is the dimension of the domain. Then the dimension of the first, I should say N1, dimension of the first hidden layer is N1, and then N2 and so on. So over here in this sort of conceptual picture, here's Rn0, Rn1, etc. And then we get to the output, which is Rnd. So that's my notation. So the map from each layer, each Euclidean space to the next is affine linear, which, what does that mean? It means it takes a vector with ni minus 1 coordinates, and it acts on it by a matrix where the entries are weights denoted by W's and biases, which I'm denoting by B. And so it acts by multiplication. So I take my vector and I stick on a 1. So what this is just doing is it's just a linear map, but I have these offsets given by the biases. And so that's the A of each map. Sigma is my notation for the ReLU function. So ReLU, rectified linear unit, as you probably know, or have heard. It's just the function that takes a real number x and outputs the max of 0 and x. So here's my graph showing what ReLU looks like. As you can see, if the x is negative, it's just the 0 function. And then for x that are positive, it's the identity function. And so sigma is my notation for the map that just applies ReLU to each coordinate. So from each hidden space to the next, I do an affine map followed by application of the ReLU function to each coordinate. So this is the sort of type of object that my talk today is going to focus on: feed-forward ReLU networks. So why study feed-forward ReLU networks? Why should we care? So I want to just take a moment to hopefully convince you that this is a worthy thing to study. And so I'm going to break it up into two pieces. There's the ReLU part, and then there's the feed-forward part. So by feed-forward, what I really mean is just a fully connected network with no skip connections, no residual layers, just straightforward, fully connected neural network. All right, so why ReLU? So first, the ReLU activation function is used commonly, and it generates really nice results. Second, the ReLU neural networks, when you use the ReLU activation function, the types of functions that you can build are piecewise linear. And so you end up studying piecewise linear geometry. In this piecewise linear realm, sort of my mental picture or cartoon is that, it's a function that, it has these linear pieces like this. This determines a decomposition of the domain into regions on which the function is linear. So in my little cartoon, here's a region, here's a region, here's a region, etc. So there's just these different regions on which the function is just an affine map. So this gives a decomposition of the domain of the function into these union of pieces. In the more general context, it gives you a polyhedral complex. And this is nice because it's like a finite combinatorial geometric object. And it allows us to get our hands on the sort of finite or rigid nature of the functions that we can consider. So sort of the rigidity of the fact that this is a finite combinatorial object sort of mirrors the fact that there's a rigidity imposed on the types of functions that we're allowed to consider by our choice of architecture. I'll say more about this later. But I guess what I want to say is that ReLU it's really commonly used, and it lends itself to analysis by theoretical techniques using piecewise linear geometry. All right, so that's sort of why ReLU, and now why feed forward? So for me, the big reason is that it's sort of the simplest paradigm for machine learning or for deep learning. Obviously, there are many types of networks that probably the audience is familiar with: convolutional neural networks, et cetera. But to my mind, the feed-forward regime is sort of the base case. It's the vanilla case. And so when we want to start trying to understand deep, difficult things about neural networks and training, as a theoretician, I always want to start with sort of the simplest case and build from there. So that's one thing. It's sort of the natural place to start many theoretical analyses. Second, other maybe more complicated architectures often contain chunks of this form. And then sort of in a similar vein to my first comment for why feed forward is that in the past, some results have first been proved or discovered in the setting of feed-forward neural networks, And then later work has generalized them to more broad architectures. So yeah, so essentially I want to think about neural networks that are of this particular form because they're nice to analyze, and I feel like it's a really good starting point. Finally, when you combine ReLU with feedforward, what you get is a big flexible class of functions. So if you're not using the ReLU activation function, maybe any sort of non-polynomial activation function, there's a uniform approximation theory that says that you can approximate any function with a function defined by a neural network of a sufficiently complicated architecture. But it's an approximation result. For feed-forward ReLU neural networks, there's a very precise on-the-nose description, which is that the class of feed-forward ReLU neural networks with domain and Rn0 and codomain Rnd exactly coincides with the class of finitely piecewise linear functions between those two spaces. So by finitely piecewise linear, I mean just that you can chop the domain Rn0 up into finitely many polyhedra, like so in my little toy case over here, they were intervals on which the function is affine linear. All right, so we've got this really big but yet simultaneously nicely described class of functions. However, practitioners or anyone who wants to actually train a neural network doesn't get to interact with the entire class of feed-forward ReLU neural network functions at once. We're forced to look at one architecture at a time. Obviously, this is not news, but the reason I'm sort of emphasizing this is that I want to make a clear distinction between the two spaces that are determined by an architecture. So on one hand, there's a parameter space, and on the other hand, there's a function space. So by choosing an architecture, there are a parameter space, which I'm going to denote by the sort of script P. And so what is that? It's just a list of the weights and biases that determine your function. And then on the other hand, there's the actual function, the space, the collection of functions. The realization map, which is in the title of my talk, I'm going to denote by rho, right? Rho R realization, is what we call the map that takes a parameter and outputs a function. So here, whoops. Here I say, so the realization map rho, it takes a parameter, theta, that's a list of weights and biases, and gives you the function. So we, meaning people training a neural network or looking at different architectures or analyzing the loss landscape, we like to think that we're getting to interact with the space of functions when we do training, for example. But we don't actually get to touch function space directly. What we do is we access it through parameter space, right? So when we do training, we move around in the space of weights and biases. And we think of ourselves as moving around in the space of functions. But the distinction that I'm trying to highlight is that this realization map is really just a parameterization of the associated set of functions. And that all the things that we sort of want to think about, I shouldn't say all the things, but many, like the loss function, training, gradient descent, etc., they all happen in parameter space. So the question then is, how does this realization map, what does it look like? How does it relate a parameter space with the thing that's being parameterized? If you imagine you're just parameterizing any old objects, like if you're using the space X to parameterize the space Y, you want to know which points in Y does my parameterization get to? In this context, it's saying like which functions are realizable for a given architecture. And then also which points in the parameter space correspond to which points in function space. So something to just kind of keep in mind is that when you're parameterizing any object, let's say like a curve in space, like maybe here's my parameterization of a curve. It can the parameterization can double back, it can cross itself, like parameterizations can have weird properties. Many different parameters can give you the same object that you're describing. And again, if anyone has any questions or comments, please feel free to jump in. What I'm leading up to is I'm images and pre-images. So the title of my talk was, well, we had realization map, feed-forward ReLU neural networks, and then images and fibers. So another word for fiber would be pre-image. I should say, I apologize for the mix of typing and handwriting. I find that sometimes, particularly when I'm writing a lot of mathematical notation or drawing diagrams, it's just kind of more convenient to handwrite. So that's why there's a mix. All right, so images and pre-images of the realization map. So remember the realization map, you pick a parameter space, so for a given architecture, and it's the map that just takes the parameters as its input and outputs the corresponding function. So from parameter space to function space. So what is the image of this map? So remember, the image is all the things you get out of the function. So the image of this realization map is just the set of all of the functions that you can get on that architecture. So for each architecture, obviously, we're kind of like carving out a chunk of the space of all functions. And I'm asking, or when I refer to the image, I'm saying, what is that chunk of realizable functions? So that's the images. And then pre-images. So the pre-image, or equivalently fiber, just two different words, of a function from, say, Rn0 to Rnd. Actually, that doesn't really matter. So you've got some function. So it's a point in the space that rho is parameterizing. So some function. What I'm asking when I talk about the pre-image or fiber is, given a point in function space, which points in parameter space get sent to that function? So that is formally the pre-image or fiber of a function under this realization map is the set. So rho inverse, meaning all the pre-images, all the parameters in parameter space that get sent to that function. So another way of saying this is that the fiber of F is all the parameter settings theta that determine that same single function F. I'll say that give rise to F. If I think back to my sort of cartoon picture of a curve being parameterized in space, I was like, well, I guess it was right where I wrote that. You have some curve that's going through space. It's like if you say, here's a point in space, which parameters gave me that point? So what I'm asking is, which parameters determine a single function? So the remainder of my talk is going to focus on these two aspects of the realization map. The image, meaning the collection of functions you can get out, and then the pre-images, all the parameters that give you a particular function. So I'm going to start with fibers or pre-images. And I want to do just an example. So I'm talking about the architecture 1,2,2,1 in this example. So that is my domain is R1, R1. Then I have two hidden layers that are each R2. And then the output is just R1. So this is not a particularly exciting architecture, but it's sort of a toy example that will allow us to see some things. Specifically, what I want to show is that I'm going to construct two different parameters that both give you the same function. The function that sends x to the max of 0 and x plus 1. So here's the graph of the function. Right, so it's 0, and then when you get to -1, you just start going up with slope 1. And I want to show that there's two very, well, really there's many different ways to build this function, but there's two that I will highlight, two different parameters that give you the same function, that do it in very different ways. So here's one way to achieve this function. Essentially, in my notation, it's sigma of sigma of sigma of x plus 1. Now, how do I achieve that? What does that mean in this architecture? That's what this picture here, what this sort of schematic diagram is meant to represent. So what I start with x, and what I want to get out is the function max of 0 and x plus 1. Here's how I can do that. So my first layer that goes from R1 to R2, I can just take x and send it to sigma of x plus 1. Then for the second neuron, I just send it to 0. And then essentially, I just sort of keep this second coordinate being 0. So the matrix corresponding to this first layer would be 1, 1, 0, 1. It sends x to x plus 1 in the first coordinate, and then just 0 in the second coordinate. And if we just kind of keep zeroing out this second coordinate, here's the second hidden layer, and then we finally get the output layer, what we get is sigma of x plus 1, which is exactly the function max of 0 and x plus 1. Okay, the details of this don't particularly matter. Just that the point was there's some function that we want to get. Here's a way to achieve it within the architecture. And it was a fairly simple way to get the function. In fact, we basically just like ignored the second coordinate. We kind of didn't use it in this particular way of building a function. But on the other hand, here's another way to get exactly the same function in the same architecture. Well, it's this expression. And let me try to sort of talk through what this is. You start with x, and so in this first layer map, so into the first hidden layer, in one coordinate, we just do ReLU of x. In the other coordinate, we do ReLU of -x. So this graph right here is the graph of ReLU of -x, right? Because if negative x is a negative number, the ReLU just makes it 0, and then we get this graph. For our second layer map, we're not going to do anything to the first coordinate. So this neuron here assigns weight 1 to this coordinate and 0 here. So it's just giving us the function ReLU of x. But for the second coordinate here, what we're going to do is we're going to take this output, flip it by a -1, add 1, and then do ReLU. The graph of this total function looks like this. If we now construct our final map to the output layer by adding this graph and this graph, you can see that where this becomes flat is exactly where this slope part kicks in. So when you add these two together, you get this function, which is precisely max of 0 and x plus 1. Okay, that was a kind of a lot of fiddly little details. The point is we built exactly the same function, but we did it in a sort of very complicated way in the same architecture. So there are very different ways to construct the same function. So hidden symmetries is a term that's gotten a fair amount of mileage in the deep learning community recently, and there's a big body of literature that I should cite. But I wrote it here because what I want to highlight is that this is an example of a hidden symmetry. That is, there's a symmetry in that there's multiple different ways to build the same function. And it's a very kind of complicated issue of which parameters can give you the same function. Okay. Let me now give you another example. So this is like the simplest architecture possible. Again, I'm just kind of doing it as like a toy example because I think this illustrates a broader concept. So the architecture is 1-1, literally the most boring architecture possible. That is, you take a parameter, AB, so the parameter space has 2 coordinates, and this determines the map that takes a point X and sends it to AX plus B, and then you apply ReLU. So the realization map goes from parameter space and outputs this function. So row of the parameter AB is this function. All right, so here are 2 different points in parameter space that give you the same function. And actually what they give you is the 0 function. The first one, which I'm calling theta1, is the parameter 0, 0. So A and B are both 0. So it's the map that takes X and sends it to 0 times X plus 0, and then you do the ReLU. So it's the 0 function. The second parameter, theta2, has 0 as the X of the A and -1 as the B. So again, you get the 0 function. So 2 relatively boring ways to build the 0 function. The reason I'm bringing up this example is I want to use this as an opportunity to think about which functions are realized by parameters near theta1 and near theta2. And what I want to argue is that even though theta1 and theta2 give you the same function, their nearby functions are very different. So here's one way to think about this. So theta1, that's just 0, 0. It has the following property. If I give you an epsilon greater than 0 and some open neighborhood of that parameter, theta1, so it's in parameter space. I'm just saying this, you can perturb, there's some number theta epsilon 1, and then I'm going to allow myself to perturb my parameter choice. My claim is that within that neighborhood, so under suitably small perturbations of my parameter, there's a different parameter choice, which I'm going to call little u, that has the property that the function it determines, rho of u, when you evaluate it at x, is positive for some x, that should say, where the absolute value of x is less than epsilon. So let me just think that through. So if here's my coordinate system, the graph of rho of theta1 is just the 0 function. However, if I perturb my coordinate 0, 0 just a little bit, for example, I could change the b coordinate a little bit. Now the graph of the function is positive. It has the property that for some small x values, the function is positive. If we now instead think about theta2, this property that we just described, that like nearby parameters give you functions that are positive near 0, this property does not hold. That is, given a sort of epsilon greater than 0, in any arbitrary or sufficiently small neighborhood of that parameter, any like nearby parameter is going to assign 0 to any input x that's small. So let me like draw a picture. Right, so here's my coordinate axes. Theta 1 is it has slope 0 and bias -1. So the graph, before I apply the ReLU, is just sort of like this horizontal line at y value -1. If I perturb the bias a little bit, maybe now it's, -0.9, the ReLU function, the sigma, is still just going to make it the 0 function. If I perturb the slope a little bit, so instead of being a horizontal line, the graph is now, ever so slightly sloped upwards, for example, I will eventually get some positive outputs, but they're not going to be near 0 if my perturbation is really small. So what's going on here? We have two different parameters that both give you the same function, in this case, the 0 function. But if we look at the functions that we can achieve near the parameter theta 1 and compare it to the functions that we can achieve near parameter theta 2, we see that these are two different collections of functions. And this is just a particular property showing or proving that these two collections of functions are different. Okay. So this was a very, just kind of like a toy architecture, very simple architecture. 1-1 could not be more simple. But we can take this example as indicative of a larger phenomenon, that within an architecture, you can have two parameters in the same fiber, meaning two parameters that determine exactly the same function, but their nearby functions are different. So that's the take-home message. You can have parameters determine the same function, but functions that are realized near the first is not the same as functions that are realized near the second. Okay. Another way to just sort of rephrase what we just said is in terms of the symmetry group. So recall that P is my notation for parameter space. So the symmetry group of parameter space, this is like for a fixed architecture, is the group of all homeomorphisms, tau, of the parameter space, such that the realization map is the same as doing, let's just say tau, first doing tau, and then doing the realization map. Two well-known symmetries are rescaling and permutation. So it's saying this tau, it's like you give it one point in parameter space, and the tau determines a different point in parameter space. For example, maybe theta 1, and then you apply tau to theta 1, and it gives you theta 2. The point is then that the realization map at those two different places are the same. So essentially the symmetry group is just all the homeomorphisms that don't affect which function you realize. They're invariant on fibers. So a way to rephrase this phenomenon that we just saw in this very simple example is that there exist fibers on which the symmetry group does not act transitively. So there's two, or well, at least two consequences that I want to highlight. One is that there's a branch of, or a direction of research, which I think is a great direction, which involves saying, given that we know that functions are represented in multiple ways, let's try to understand all the ways that functions can be represented in different ways and quotient parameter space by that. In other words, look at a smaller subset of parameter space, since we know that there's this redundancy. What this proposition is saying is that because 2 points in a fiber have like different sets of nearby functions, we're never going to be able to obtain the collection of functions as a true quotient of parameter space. The other thing I wanted to mention was another ongoing branch of research, or getting some mileage, which is teleportation. Which is, what is teleportation? It's the idea that when you're doing training, you're training a neural network. When you get to some parameter during the training process, maybe instead of continuing the training process from that parameter, instead you want to jump or teleport to some other parameter that gives you the same function and continue on from there. What this example or this proposition is saying is sort of giving us a reason to believe that teleportation might be advantageous, that you can represent a function in multiple ways, but from the point of view of where you can go after that during training, not all parameters are equal. My collaborator, Ellie Grigsby, actually spoke in this seminar maybe a month or so ago, and she talked about the notion of functional dimension, which we've been studying. I just want to mention it briefly. So we defined this notion of functional dimension of a parameter, and what it is, roughly speaking, is that if you look at the collection of functions you can obtain by perturbing the parameter, so just changing your parameter ever so slightly, what's the dimension of the space of functions that you can achieve? So for some parameters, if you perturb the parameter, you can't change the function very much. Like we saw that, for example, in this example where the function was, the parameter was 0 and -1. Basically, no matter how we perturb it, we're just always going to get out the 0 function. Whereas for this parameter, if we perturb it a little bit, we actually can get a whole bunch of different functions. So here, I would say there's a 0-dimensional space of functions that you can achieve by perturbing the parameter, because you just can't change a function. And here, there's actually a 2-dimensional space of functions. I'm not going to go into this in much detail, but as sort of to complement this collection of results that I'm describing, I wanted to mention this proposition, which is that there exist fibers on which functional dimension is non-constant. So that is, just as in this example up here, you can realize a function in 2 different ways. And not only can the collection of sort of nearby functions be different, they can be different dimensions. So this is another result in the direction of saying not all parameters are equal. All right, so within a fiber, all the different parameter choices that give you a function, some parameters are kind of different properties than other parameters. What about the structure of the fibers themselves? So here's a proposition: disconnected fibers exist. So remember, what is the fiber? It's all the different parameter settings that give you a particular function. What this is saying is that if you look at that set of parameters, maybe it's not even like one blob of parameters. It could be 2 disconnected, or more than 2 disconnected regions. The proof of this proposition is again by example. It doesn't matter too much exactly what this example is, but just here's a function. The function x goes to absolute value x in some particular little toy architecture. And there's a parameterization of it in terms of weights and biases, which I'm calling A, B, C, D, et cetera, up through G. And I'm not going to work through this now, but if you carefully think it through and make a rigorous argument, you can precisely describe the fiber of this function. And it consists of two pieces. Well, here are the parameters, and then here's the conditions. And these are actually all the same until you get to this last part. The only place these two things differ are here. Here in this set, FC is -1. And here the product FC is +1. So if I only draw the FC plane, I'm just ignoring the rest of this parameter space. I'm just drawing the FC slice of parameter space. There's sort of a part of the fiber where the product is +1, and there's a part of the fiber where the product is -1. So I think this is really interesting because it's really saying that the way the parameterization of function space by the parameter space works is really not straightforward. There's a rich geometry inherent in the question of like which parameters give you a particular function. All right. So I have this slide sort of summarizing some key takeaways of what I wanted to say about fibers. And this is a typo. It should say injective. So the first, this realization map is not injective. Right, injective just being the fancy way of saying that, well, not injective, meaning that you can have different parameters give you the same function. But then when you actually look at which parameters give you the same function, fibers, these objects have very complicated topological and geometrical structures. And different points in a fiber can have very different properties in terms of what their sort of neighborhoods look like. So that's kind of summarizing what I've said so far about fibers. But no, I want to argue that I believe that understanding how parameter space is built out of fibers is really inseparable from the question of understanding the dynamics of the training process. And I like cartoon conceptual pictures. So here's a cartoon picture of a fiber where in my sort of cartoon, the parameter space is R2. So here's my R2 axes. If I draw all the parameters that give me the same function, the fiber, maybe it's the set that looks like this. It has all these multiple different pieces, and the pieces might even be of different dimensions. Like over here, here's this sort of 2D chunk where all these parameters give you a single function, but over here it's like 1D, and over here maybe there's just some isolated parameters. This picture has implications for training because when we think about trying to understand what the process of training a neural network does, like which types of functions it tends to pick out and how the training process moves through the space of functions, what we're really doing is we're moving in parameter space. We're not moving in the space of functions. So, imagine it's just kind of a thought exercise. If you initialize your training at some point over here, maybe I'll use a different color. Maybe you initialize over here at this purple point. And maybe the point that you really want to find is, say, over here. That's your best solution. In order to get there, you would have to cross this fiber. So fibers could form barriers. The other thing is, maybe you somehow end up inside here, and there's just no way you can move to change your function. Because all these parameters represent exactly the same function, the loss function will be flat on the fiber. And there's, I guess, a growing body of research trying to understand how the structure of minima of the loss loci, where the loss function is minimized, is related to like how well the function does, how well it generalizes and other properties. And so I think this this question of fibers has a lot of implications for that. All right, I need to move along quickly. So that was all sort of part one, fibers. The other half of my talk, which I'm not going to have time to get through, is the image of the realization map. So I'm going to go fairly quickly here, but the question is, how does the architecture constrain the set of realizable functions? Now, of course, we need architectures because, by focusing on a particular architecture, well, one thing we're doing is we're avoiding crazy over parameterization or under parameterization. We're taking that incredibly broad or flexible class of all functions and we're narrowing down to a particular set of functions. Folks who do, architecture search spend a great deal of time, I understand, investigating the really interesting question of like which architectures tend to have collections of functions that are useful. So that's in my language, what I'm saying is, what is the image of the realization map? And there's various notions of complexity that you can use to describe functions. Some well-known ones are shattering or VC dimension. For linear ReLU feed-forward neural networks, you can ask about the number of linear regions, etc. I am particularly interested in topological notions of complexity. So if you have a function, f, say the domain is Rn and it outputs numbers, you can form decision regions by you take some threshold t, and you look at the 3 different regions where the function, like n for no, where the function takes values lower than t, b for boundary, where the function takes the value exactly t, and then like y, yes, where the function takes the value greater than t. I think it's pretty natural to ask about the topology of these decision regions and sort of how flexible can the topology be? So I think of this as topological expressivity of the function. So asking, how complex are the functions that we're building from a topological point of view? So a theorem that I find very inspiring, proved independently by three papers, is the following. If you fix an integer n greater than 2, and you look at a function from Rn to R that is a feed-forward ReLU neural network, and here's the constraint, whose hidden layers all have dimension less than or equal to n. So your layers are not allowed to get wider than whatever your input dimension was. The conclusion of this theorem is that for any threshold, if you look at these decision regions, each decision region is either empty or unbounded. So just to make this concrete, what this really cool theorem is saying is that in this setting, meaning all the hidden layers have dimension less than or equal to the input dimension. In this case, like if I envision n as being 2, again, like toy examples, this blue region that I've drawn here in R2 could not be a decision boundary because it is bounded, meaning you can't go off to infinity in any direction. And indeed, nor could this, or this, or this, just simply because they're bounded. So this is an example of a topological constraint on the function that's imposed by the choice of architecture. In the same vein, another result that I proved together with my collaborator, Ellie Grigsby, is for architectures of the form n plus 1, and 1. So again, a fairly simple sort of architecture. The the conclusion is that in this case, each decision region has at most one bounded connected component. So for example, in this architecture, if we were doing 2, 3, 1, here's my R2. If I have, say, like this region and then like this region, that set could not be a decision region because it consists of 2 different bounded pieces. So it's just another example of a topological constraint on the function that's imposed by the architecture. And you can push this further. I know I'm running out of time, but so in a joint work with Grigsby and Marsden, I was looking at something called homological complexity, which is a related idea. It's sort of asking, as you vary the threshold, how does the topology of the decision regions change? And can we record this using algebraic topology? And so here's a picture of the graph of a function of one variable, same graph repeated 3 times. In the leftmost picture, the threshold I've chosen down here has the property, if you look at where is the function, where's the sort of no region corresponding to that threshold, it's this just one unbounded interval. However, if I pick my threshold like here, for example, and I ask, what's the no region for that threshold? So where is the graph lower than t? Now there's 2 different intervals. There's the same unbounded one to the left, but now there's the second region here. And then, as your threshold increases even higher, you return to, having just a single component, connected component. So you can sort of ask questions about how these thresholds change and record the results using ideas from algebraic topology. I think that these sort of topological constraints are nice in that they do not depend on anything about the parameterization of your space. So, when you're putting coordinates on your data space or looking at, maybe a manifold where the data lies, these sort of topological things are coordinate independent. So they're giving constraints that are yielding constraints that are, very, very strong in the sense that they're up to like topological equivalence. And I think I should end, but I'll just say briefly, I just want to mention this briefly, is that feedforward ReLU neural networks can have bounded images. So for example, here's a function where the domain is R2, there's one hidden layer and the output is R2. And well, maybe this isn't super clear, but I start with the whole plane R2. If my first map is just the identity map, when I apply the ReLU, the image is just the quadrant where all the coordinates are non-negative. For this final layer map, if I sort of pick these to become my new, define the map, the weights and biases, so that these become my new coordinate axes, the image of R2 is just this little bounded region. So this is kind of maybe surprising that the image of maps of this form can be unbounded or bounded. And so something I'm thinking about now, work in progress, is like, how likely is it, given an architecture, that a function realized by that architecture has a bounded image? Or another direction is, if it's unbounded, in how many different directions is it unbounded? And answers to these questions will have implications for the topology of decision regions, and thus for architecture selection, since when we pick architectures, we want to pick architectures where the functions, are sufficiently rich, but not too rich to model whatever phenomenon we're trying to describe. And we've done some experimental work. I'm just going to skip that. And I'll just sort of briefly conclude. I did takeaways of fibers. Now I want to say takeaways of the realization map. So my first point is that the subset of function space realized by a given architecture is still mysterious. It would be good to have some nice concrete way to say, if I give you this architecture here, in whatever sense of here are the functions you can get using that architecture. Second point, boundedness of the image, or sort of like collapse of regions as you move through layers, is kind of a ReLU phenomenon related to the fact that the ReLU activation function truly is 0 on a region. However, when you think about using other types of activation regions, activation functions, like for example, something represented by this picture where you have sort of asymptotes. When you actually do anything with this, computers treat asymptotes as flat functions for large enough values, because we have to do numerical approximation. So even functions like this in practice, when we're actually computing things, have the same collapse sort of phenomenon. So so aspects of the ReLU function actually have ramifications for other types of things. And then finally, just that I think it's an interesting direction is that understanding how this topology of decision regions depends on the architecture, and that topological notions of expressivity are yielding interesting results that may have applications or implications for architecture selection. That's it. Thanks.
Thank you, Kathryn, for this great talk. Let me first stop recording.